When you attempt to measure out exactly 0.003 grams of a fine powder, the material often behaves like it's magnetized. Instead of falling onto the pan, the particles remain stubbornly clinging to the tool. It's a common frustration in the lab. Even after wiping every surface down with a dryer sheet, the powder continues to defy gravity. This usually triggers a series of desperate DIY fixes, like placing a damp Kim wipe inside the draft shield to manually jack up the local humidity. Meanwhile, the hardware provides no clarity. The digital display bounces erratically from 0.002 up to 0.01, never locking in on a stable reading. At this microscopic scale, the invisible forces of the environment override the physical weight of the sample. Standard home remedies are technically incapable of neutralizing these forces. The air inside a laboratory is a shifting mixture of positive and negative ions. In a confined space, these charges frequently fall out of alignment. This creates an ion imbalance, where one specific charge heavily outweighs the other. Analytical balances are built from non-conducting materials like glass and plastic. These materials act as insulators, trapping the unaligned charges within the weighing chamber. This creates a chaotic electrostatic field that disrupts the otherwise sterile environment of the scale. These trapped charges on the draft shield exert measurable physical force on your sample. The electrostatic field is pulling and pushing on the powder particles with enough strength to rival the force of gravity. These forces extend beyond the sample, interfering with the balance's internal load measuring mechanisms. This chart shows the resulting multiplied repeatability error. Because the scale sensors are picking up the shifting electrostatic forces instead of a constant mass, the reading appears as an unpredictable wave rather than a flat line. The drifting numbers confirm the scale's high level of sensitivity. It is accurately recording the invisible electrical chaos of the room. To achieve stability, you have to actively manage that environment, using a tool like the Radwag DJ-05 anti-static ionizer. This device uses a stainless steel ion source to project a controlled stream of both positive and negative ions directly over the scale pan. As this stream fills the weighing chamber, it seeks out the excess charges clinging to the glass, the plastic, and the sample itself, neutralizing them on contact. This process creates a quasi-balance, a state where the positive and negative ions in the air are perfectly equalized. With the ions balanced, the invisible forces pulling on the sample are eliminated. When we re-examine the weighing process with the DJ-05 active, the environment is now fully neutralized. The sample now behaves predictably. The powder releases from the spatula and falls straight to the pan without any residual clinging. The digital display locks onto the target mass instantly, ending the phantom drift and bouncing numbers. The balance is now measuring only the vertical force of the sample's mass, free from electrostatic interference. Precision metrology requires moving past the guesswork of dryer sheets and DIY hacks toward hardware-driven standards. A perfectly calibrated balance is ineffective if the atmosphere inside the draft shield remains unmanaged. Modern research and quality control rely on managing the invisible environment of the lab with the same rigor applied to the physical samples. True accuracy is achieved by pairing a calibrated scale with a balanced atmosphere.